right, so we started with the 1-4 quick review. We don't actually learn 1-4 because we don't need to do parametric since we are not teaching CHS. So if we went the CHS route, then we would do 1-4. However, the quick review in 1-4 is a really nice review of some of the skills and sets we do use, which is function composition. So, sorry, I should have told you to skip 5 and 6, as those were parametrics, but you could do 1 through 4. So to find f of g of 1, you plug the number 1 into g to start, and then you get that number, which is 2, and then you plug 2 into f, and get the cube root of 1. The cube root of 1 is 1. So that is why f of g of 1 is 1. And number 2, you'd plug -7 into f to start. So you get the cube root of -8. Now remember, you can take the cube root of a negative because it's odd. So the cube root of -8 is -2. -2 then gets plugged into g. A negative number squared becomes positive. So you get 4 plus 1, which is 5. Number 3, same idea. So the difference from 1 and 2 to 3 and 4 is that 3 and 4 are in terms of a variable x, where 1 and 2 are in terms of a number. So when you're looking at these problems and you're using a number, you will get a number as part of your answer. If you look at a function composition with a variable, you are going to get variables in your answer. So that's why for number 3, we get x to the 2/3. And in number 4, you get x minus 1 to the 2/3 plus 1. Okay, in 7 to 10, you are looking for points of intersection. So in 9 and 10, you would need to put those on a graphing calculator. But 7 and 8, you should be capable of finding your points of intersection algebraically. So this is kind of like using substitution. You get y equals 2x minus 3 when y is 5. So that means that 5 equals 2x minus 3, or that 8 equals 2x, or that x equals 4. X equals 4 when y is 5, hence the point 4, 5. Similarly, in number 8, you'd have y equals -3x plus 5, y equals -3, so you'd get -3 equals -3x plus 5, and then you'd subtract your 5 and get -8, -3x, or that x equals 8/3. For 9, 10, A and B, these ones would need to be done on a graphing calculator. So in order to do these on a graphing calculator, you would have to plug the first part into y1, plug the second part into y2, and then look for their point of intersection using second trace. If we can't find a point of intersection, then we write none. And again, we know that B are none because the domain of y equals 2 to the x is all reals. However, the range of y equals 2 to the x is 0 to infinity because you cannot plug any number in for the exponent on 2 and get a negative value. Even if I plug in like -5/3, you're still going to have a positive 2 value because all it does is flip it and turn it to a fraction. So again, this comes from our idea or understanding of domain and range for an exponential. And that was part of what we talked about earlier in the week. So we are going to look at some basic definitions today. The first thing we're going to talk about is a logarithm. A logarithm-based function is a function in which we have a positive real number other than 1. And the base of that exponential is a. So anything a to the x is considered a logarithm function with a base that is an exponent. We know that a to the x is 1 to 1, and its inverse is going to be a variation of that. So essentially, to find the inverse of a function, we know that we flip x and y. So this would be like saying x equals a to the y, and you want to try to get y by itself. Well, we know that we can rearrange or get that y away by multiplying both sides by 1 to the y. But that doesn't help me because I can't solve for an exponent of 1 to the y. And that's where the idea of a logarithm comes into play. So we know that the inverse of a to the x is y equals log a to the x. So y equals log a to the x is the inverse. And we get that by taking the log of both of those sides. The property of logarithms allows us to bring our exponent down in front and solve. We're going to see how that works today using change of base. So the domain of the log base a of x is the range of a to the x. And the range of the log is the domain of a to the x. So in that previous warm-up example, we talked about y equals 2 to the x. Its inverse would be y equals the log of 2 to the x. And once again, the domain and range would flip just like they do here. Okay, logs with base e are known as special logs. These logs are actually on our calculator. They're the log button you see on the left where it just says log. So logarithms with base e and base 10 are considered the special logs. They get their own buttons on a calculator. We call the log base e of x the natural log, and we call log base 10 of x the common log. So the natural log is log base e, the common log is log base 10. Another way to write the inverse is a to the log of a to the x. So another way to write our inverse is a to the log of a to the x, because a to the log a cancel and you get x, just like e to the ln of x is x. E to the ln of x is x, and ln of e to the x is x. And you can check that by typing on your calculator ln e to any number or variable or to nothing, and you'll see that you end up getting back whatever you raise it to. So if you did like ln of e squared, and you type that in on your calculator, you'll get the number 2. You can also identify that using our properties. Technically, an exponent inside a natural log can be rewritten out in front, and you get ln of e. And again, ln e is kind of like saying square rooting x. They're inverse properties. This becomes 1. You get 2 times 1, which is 2. That leads into what I was just talking about. We have 3 rules. These apply to ln and logs. And our rules are that if you have the product, you can turn it to addition. The quotient becomes subtraction. And the power rule brings it down in front. So these are similar to our product, quotient, and power rules for exponentials. If you think about the product rule for an exponential, that's where you have like a to the m times a to the n. You added m and n. Here you have a, the log base a of xy. That's the same as log ax plus log ay. A really important formula, and this used to be important before our graphing calculators got smarter, was the change of base formula. So our graphing calculators, the log button limits them to a log base 10. So if you ever wanted to find the log of something other than a base of 10, you needed the change of base formula. However, now our calculators have grown increasingly smarter, and we can actually do a change of base formula on our calculators. So what I'm going to do real quick is going to show you how on our calculator they are the same, or where the new log feature is. Okay. So if you have one of these graphing calculators here, give it a second. It's being super slow. Tried to make it big. Let's try that. All right. All right, so if you have one of the graphing calculators here, like this, then what you can do on that graphing calculator is actually hit keys in here. So we're going to go to our home screen. And then what you can do is you can actually go down to math now on a graphing calculator. And if you scroll all the way down, you see log base. If you hit enter on that, yes, I know my calculator batteries are low. You'll see that now you can actually type in any log base on your calculator. So you could type in log base 5 of 5 and get an answer of 1. You can go up and you could try 5 and 8. And we see that that's 1.2920. And again, you can compare that to the change of base formula that said you take the natural log of 8 divided by the natural log of 5, because it was the inside over this. And we see that we get the same answer. So again, the graphing calculators used to not have this feature built in. You used to only ever be able to take a log base 10, which is what this key does here. But now they have this extra feature built into math. Okay. So what we're going to do today is look at some of these natural logs and exponentials, and our goal is going to be to solve for our variable x using each of these new rules. So in letter A, we have the natural log of x equals 3t plus 5. Our goal is to solve for x. So to get rid of the natural x, we're going to use the e both sides technique, because we know that e to the natural log simplifies to the inside, which in this case is x. So we get x equals e to the 3t plus 5. That 3t plus 5 becomes its exponent. And letter B, to get rid of e to the 2x, to get rid of that e, you're going to ln both sides. Because remember, in math, we have to balance our scales. So what I do to the left, I have to do to the right. The natural log and e are inverses. So it's kind of like multiplying 1/2 times 2. They cancel. So that leaves you with 2x equals the natural log of 10. Divide both sides by 2. And x equals, you can write it as natural log of 10 over 2, or 1/2 the natural log of 10. That is a numerical answer. You don't need to simplify that any further. I just want to show you a property. Remember, we said that if you had an exponent inside, you can bring it out as the number out in front. That's actually true for the reverse. So this is really the same as saying the natural log of 10 to the 1/2 power. And if you don't believe me, you can test that theory and type all of these on your graphing calculator and see that all of them simplify to the same numerical value. Okay, we have solved the following for x again. So you have 2 to the x equals 12. Well, we can't change the base for these to be the same because 12 isn't a power of 2. So we have to use the property of logs that says a to the y equals x can transform to log base a of x equals y. So a to the y equals x becomes log base a of x equal to y. So that means that the 2 is like my a. So this becomes log base 2. The 12 is my x. And the power x is kind of like my y. So I get that x equals log base 2 of 12. And again, the idea is that that is just a number. You could go to your graphing calculator and do natural log of 12 divided by natural log of 2. You could use the change of base log solver now in the math feature. But this is really the same as x equals 3.585. We've solved for x. X is a numerical number. Okay, e to the x plus 5 equals 60. Solving for e to the x is kind of like solving for an absolute value. We need to isolate e to the x. So we're going to subtract 5 from both sides. So we get e to the x equals 55. And again, the inverse of e is ln. So you'll ln both sides, and we get that x is equal to the natural log of 55. It's important to know that the natural log of 55 is just a number. This is considered what we call in math a constant. The natural log of 55 is a number. It is a constant. Okay, the population P of a city is given by P equals 105,300 e to the 0.015 t, where t equals 0 represents 1990. According to this model, when will the population reach 150,000? So what we want to do is look at that and figure out, okay, what am I looking for and how do I go about finding it? So we are looking for the p-value of 150,000. So we're solving for time. So we got 150,000 equals 105,300 e to the 0.015 t. We're going to divide both sides. So we can isolate our e. When you're dividing like this, if you have zeros at the end, they cancel. So really this is the same as 1,500 divided by 1,053. And if you have your calculator, you're going to ln both sides. So that we get the natural log, and I simplified my fraction to 500 over 351 equals, the e is gone, 0.015 t. Solving for t, you divide by both sides by 0.015. So plugging in, you get t equals the natural log of 500 over 351 divided by 0.015, or 23.588. Remember, everything in calc is 3 decimals. That 23.588 represents the number of years after 1990. So if it says when, it's not looking for 23.588. It's looking for the number of years or the year at which that occurs. So that would have been 2013, and the 0.588 would represent the number of months into the year. So you could convert that into months by taking 0.588 times 12. So you're 12 months in the year, and you get 7. So 23 years later would be in 2013. And if you want to be specific, in month 7. So month 7 is July. So the population would reach 150,000 in July of 2013. That's how they're looking for your answer. They're not looking for the 23.588. They're looking for you to interpret, what does that 23.588 mean? It means that in July of 2013, the population will reach 150,000. You need to get into the practice of writing down that type of sentence. So it would say in July of 2013, the population of city P would be 150,000. Okay, so the homework is in the book. We're talking about page 44 to 45. You're looking at the 32 to 42, 51, and 59 to 62. I did write down this equation because I believe you need it for one of the problems. So this equation is a compound interest formula where A is what you acquire, P is your initial investment, R is the rate as a decimal. So like if the rate was 5%, the R value you plug in is 0.05, and M is the number of compounds. So if something is quarterly, then that's 4. If it's semi, that's 2. Annually would be 1. Monthly would be 12, and so on.